Hey everyone, and welcome to today's Explainer. We're going to dive into what I think is one of the most literally mind-bending phenomena in electrochemistry. We are breaking down the mechanics, and yeah, the math, of concentration cells, so you can absolutely crush your upcoming chemistry final. Now, if you're already feeling pretty good about standard galvanic cells, well, concentration cells might actually throw you for a loop at first. But don't worry. By the time we wrap up here, you're going to see exactly how elegant and honestly predictable the whole shebang really is. Let's get into it. Here is our quick roadmap for today. We'll start out with the core paradox, peek inside the half cells, calculate the potential, lay down the rules of spontaneity, explore the power of ratios, and then finish up with a final exam checklist.
Section 1, the paradox.
Okay, so let's start with a setup that kind of seems to break the fundamental laws of electricity. Normally, right, in a standard galvanic cell, you need two totally different metals, say zinc and copper, to get a potential difference. But in a concentration cell, both electrodes are literally the exact same substance. So, if a cell needs a potential difference for electricity to flow, how on earth do two perfectly identical solid copper electrodes generate any measurable voltage? It's kind of like trying to get water to flow between two completely identical level buckets. Without a tilt, there's absolutely no reason for it to flow. And yet, in our cell, electricity flows for sure. Section 2, inside the half cells. To solve this little mystery and find our missing tilt, we really need to zoom in and look at what's going on inside those beakers. Both electrodes are solid copper. They are physically 100% identical. The real secret, it's hiding in the liquid they're sitting in. The solutions only differ in their molar concentrations, which we're calling M1 and M2. Now, to make this super easy to visualize, imagine M1 and M2 are two adjoining rooms hosting a party. M1, it's pretty dead, just a few people scattered around, that's our low concentration. But M2 is absolutely packed, shoulder to shoulder, a super high concentration. Naturally, if you throw open the doors between those rooms, people are going to flood from the packed room into the empty one just to get some breathing room, right? That fundamental desire for balance is exactly what creates the potential difference in our cell. Let's break down the actual chemistry making that balance happen. Over on the anode side, the negative one, solid copper gets oxidized, pumping out more Cu2+ ions and freeing up electrons. This happens in our M1 solution. Meanwhile, on the cathode side, the positive electrode, those packed Cu2+ ions in the M2 solution are getting reduced, soaking up electrons to turn back into solid copper. Now listen up, because mixing these two up is a classic mistake students make on exams. To lock this in, use this super simple mnemonic rule. Anode is paired with M1, and cathode is paired with M2. Think about it alphabetically and numerically. A for anode comes before C for cathode, and 1 comes before 2. So the anode creates the M1 concentration through oxidation, and the cathode consumes the M2 concentration through reduction. Just keep those pairs glued together in your brain. Section 3, calculating cell potential. All right, so now that we've got the physical setup down, let's prove how this actually makes voltage. By mapping out the net reaction, which is really just Cu2+ ions migrating from the packed M2 state to the empty M1 state, we can build our cell potential calculation. Just like any other cell, you find the total E cell by taking the cathode's potential and subtracting the anode's potential. To do that, we expand the standard Nernst equation for both sides and plug in our M2 and M1 concentration logs. Simple enough, right? But here comes the math plot twist. When you expand that formula out and do the subtraction, the standard cell potential, the E0 value, is sitting right there on both sides of the equation. And since both metals are solid copper, their standard potentials are literally exactly the same. So E0 minus E0 is just 0. Boom! They cancel out completely. This is huge because it mathematically proves that the metal itself isn't driving this battery. The concentration difference is the one and only thing pushing that current. So, once those standard potentials vanish and we combine our log terms, we are left with this beautifully simple formula for cell potential at 298 Kelvin. E cell equals 0.0591 divided by N, all multiplied by the log of M2 over M1. And just a quick refresher for your notes, N is simply the number of electrons swapping hands in the reaction. In our copper cell, since copper goes from solid to Cu2+, our N is exactly 2. Section 4, Rules of Spontaneity. Okay, here's an absolutely crucial point. For any electrochemical cell to fire up and run spontaneously, that overall E cell value has to be positive. There's no way around it. Look at the log ratio of M2 over M1 in our formula. For that whole chunk of math to end up positive, the number inside those parentheses has to be greater than 1. And what does that mean in the real world? It means the concentration of M2 must be strictly greater than M1. It's that simple. The spontaneous reaction has to flow from the crowded room, M2, into the emptier room, M1. That flow is the engine of our whole cell. But hey, what happens when those two rooms finally balance out? When the concentration of M1 is exactly the same as M2, that ratio becomes exactly 1. And the log of 1, it's 0. Multiply anything by 0, and you get 0. The voltage drops right off a cliff, and the battery is completely dead. No electricity flows whatsoever. And honestly, it's pretty cool, but this exact principle of finding ion balance is the fundamental mechanism behind everyday tools like pH meters that measure acidity. Section 5, the power of ratios. Let's actually plug some numbers in and see this math do its thing. To make it super easy, we'll assume n is 1 for a second. If your M2 to M1 ratio is 10 to 1, like say 0.01 over 0.001, the log of 10 spits out a baseline cell potential of about 0.0591 volts. But check this out. What if we crank up the M2 concentration and make that ratio 100 times stronger? That's 0.1 over 0.001. The log of 100 is 2. Multiply that through, and suddenly your cell potential jumps to 0.1182 volts. Think about that for a second. By increasing the concentration ratio from 10 to 100, you literally double the overall voltage output of the cell. How cool is that?
But hold on, we do have to remember that this high voltage doesn't last forever. Picture those ions actively surfing back and forth between the half cells. The anode is constantly churning out new ions, so M1 keeps creeping up. At the exact same time, the cathode is gobbling ions up, so M2 is dropping. They are on a collision course, continuously shifting toward each other, until they finally meet in the middle, hit that equal concentration, and flatline at that zero voltage equilibrium we talked about earlier.
Section 6, Final Exam Review Checklist.
Wow, okay, we have covered some serious ground today, from physical bucket analogies all the way to log ratios. So let's wrap all this up into a rapid-fire review checklist for your finals. Seriously, jot these down. This is basically your cheat sheet. Number 1, the electrodes have to be the exact same metal. Number 2, the solutions differ only in their molar concentration. Number 3, remember her little trick? A before C, 1 before 2. M1 is the anode, M2 is the cathode. Number 4, mathematically, those standard cell potentials, the E0s, cancel out completely. Number 5, lock this one in. The reaction is spontaneous only if M2 is greater than M1. And finally, number 6, when those concentrations finally equalize, your voltage drops to a hard 0.
All right, let's finish up with a quick thought experiment just to test if you've really mastered this before exam day. Imagine someone sneaks into your lab and messes with your setup, and suddenly, the concentration of the anode solution, M1, is strictly greater than the cathode solution, M2. What happens? Well, think back to our simplified formula. If M1 is larger, that M2 over M1 ratio turns into a decimal less than 1. And what's the log of a decimal? A negative number. That means your entire overall E-cell voltage flips negative, and the forward reaction is completely, absolutely dead in its tracks. But it raises a really wild question. If the forward reaction is dead, does the cell just give up and stop entirely? Or does the chemical universe literally throw that battery into reverse to find its balance? I'm going to leave you to chew on that reversal as you study. Thanks so much for hanging out with me for this explainer, and seriously, best of luck on your exams. You've got this.